Now that we've seen how to add, subtract, and multiply vectors, we're going to look at some applications. This video will only deal with relative motion, but our other applications will be how velocity and acceleration vectors are related in general, projectiles, and uniform circular motion. Before we move into relative motion, first thing I want you to do is see if you remember the law of sines. So enter that into the little box on the side. Now, the law of sines, if you don't remember, is that the ratio of the sine of this angle divided by the length of the opposite side is the same for all the angles in a triangle. We will find this law to be extremely useful when adding vectors graphically. Now, before we look at relative motion, the first thing I want to do is simply review a little bit about how boats move through water. Essentially, what they do is they push some water backwards, and that propels the boat forward, and that propels it forward along the length of the hull, which is what has been outlined here with the red arrow. That, of course, relates to rowboats and powerboats. We're not going to worry about sailboats. But this will give us the motion of the boat relative to the water, because it'll be moving the water backward and therefore moving forward relative to the water. And we'll have to remember that. Now, problem will be is we can figure out how fast the boat is moving relative to the water, which is this term right here, by how fast it's moving the water backward. Usually, however, we want to know how fast is the boat moving relative to the shore, because that's where we get on the boat and get off the boat. The notation I'm going to be using is that the subscripts will tell us which velocity vector we're worried about. We'll use W for water, G for the ground or the shore, and B for the boat. And this slash will mean relative to. So the first term right here is the velocity of the boat relative to the shore. And that will equal the vector sum of the velocity of the boat relative to the water. This will often be referred to as the velocity of the boat in still water. But the water usually isn't still, so we have to add the velocity of the water relative to the ground, which is otherwise known as the current. Now these three vectors add up, which means they form a triangle. And we'll refer to this triangle as the velocity triangle. So what we have right here is the velocity of the boat relative to the water, which is this red vector right here. We add the current, which is this green vector right here, and the yellow vector is our resultant. So what we're going to do is represent this equation graphically by drawing a triangle. First thing we're going to do is watch a short video of how a boat moves in a river. Note the camera is attached to the bridge.
Floats are used to determine the current flow. Using the fixed buoys in the water as a reference frame, the current velocity can be determined from the motion of the floats.
For our purposes, only thing I'm going to worry about is the fact that the current is moving down the screen.
Going upstream. You can use a vector equation to find the velocity of the boat with respect to the water. The velocity of the boat with respect to the shore is equal to the vector sum of the velocity of the boat with respect to the water plus the velocity of the water with respect to the shore.
Here I just want you to notice that the boat is moving very slowly when going upstream.
You can use the same vector equation that you used for the previous segment. This time, the velocity of the boat and the current are nearly in the same direction.
And notice how much faster the boat went when it was aimed downstream, because the two vectors added up.
The direction that the boat is headed is not the direction that it ends up going. The boat is pointed directly across the river, yet the current carries it downstream. Using vector addition, you can determine the velocity of the boat with respect to still water.
Now here we're going to draw the vectors. So first vector we're going to draw is this is the direction the hole was aimed, which we're going to call the velocity of the boat with respect to the water. So we're going to back up the video and put the boat right there. So this is the direction the boat was aimed in. But you'll notice since we were viewing this whole scene from the camera, which is attached to the bridge or the ground, that's not the direction the boat went relative to our point of view, which is the ground. Because to that, we had to add how fast the water was moving, which was the current. And the sum of those two is the velocity of the boat with respect to the ground, and that's what we see. So what we can do is watch the boat move, and notice the boat, relative to our point of view, moves along the yellow vector while always pointed in the direction of the green vector. So this right here is the resultant of the motion of the boat with respect to the water and the motion of the water with respect to the ground, or the current, and this is what we see, but only with respect to the ground. If we were in the water just freely floating downstream on, let's say, a raft, we would simply see the boat moving away from us in a straight line in the direction that it is aimed. Now we're going to look at a different motion across the river.
In order to compensate for the effect of the current on the direction of motion, the boat must be aimed upstream to go directly across the river. Use this segment to determine the angle of attack that the boat makes with the current. Then you can determine the velocity of the boat in still water. Do your results from all 4 segments of this chapter show that the speed of the boat in still water was constant?
Now again, here what we can do is draw the vectors. So we will back up the video. So the boat is right around here. And this red vector is in fact the velocity of the boat relative to the water, which moves right along the length of the hull. So there we can see that's the velocity of the boat with respect to the water. To that we must add the current, which is the water with respect to the ground. The resultant is this yellow vector, which is what we see because we're sitting on the ground. And we will see the boat move right along this direction right here, horizontally across the screen, because we're looking from the ground. And again, the relative velocity equation can be represented as a triangle, and the sum of 2 vectors equaling a third vector. One important point, which we'll go over, is that this triangle is not the same as the other triangle. It's not the same triangle flipped over. What I want you to do now is try your hand at doing some problems. The problems are essentially the same. We're just putting some numbers in it. First thing we're going to do is consider what happens when we aim the boat directly across the river. And we have a current of 3 meters per second. I want you to find out how long does it take to cross to the opposite shore, and where does it land. Second problem is, let's say we want to start our boat right here, and we want to land right here on the opposite shore directly north from where we started out. Where do we aim the boat? And again, how long does it take to cross the shore? I want you to pause the video, spend a few minutes, try to solve these 2 problems, and enter your answers in the little box that will appear. Now, let's look at the solution to the first problem. First thing we're going to do is draw the relative velocity equation. And what we have right here, this is the boat relative to the water, which we know is headed due north, because that's where we aimed our boat, and it's going at 5 meters per second. The current is moving to the east, so we're going to add these 2 vectors together, and this will be our resultant vector. This, of course, will be a right triangle because the boat is aimed north, and the current is pushing it at right angles, basically eastward. So we have a right triangle. We can just use Pythagoras to get this length right here. Turns out that's 5.83 meters per second. And this angle right here is the direction the boat ends up moving in, and that's just the inverse tangent of 3 divided by 5, which turns out to be about 31 degrees, and it is east of north. What we're asked to find, how long does it take the boat to cross the river? Well, the river is 100 meters wide, and we're headed due north. So we are going 5 meters per second north, so in 20 seconds, we will move 100 meters north. That means it'll take us 120 seconds to cross the 100 meters of the river. Notice, while we're doing that, we're going to also be going downstream at the rate of 3 meters per second for those 20 seconds. So we will land on the opposite bank on the river 60 meters downstream, or 60 meters east. Second problem was similar to the first, but not exactly identical. So again, we're going to draw the exact same triangle, only now the 5 meters per second is going to be aimed somewhat upstream in order to let the current push us downstream. So now the velocity of the boat relative to the ground will be due north. We will leave the shore right here and we will land over here. Notice this is not quite the same triangle. This one, in fact, is a 3, 4, 5 right triangle, because now the 5, rather than being one of the sides, is the hypotenuse. That means this side right here will be 4 meters per second, which means we're now going to be going north at 4 meters per second, because we're going 5 meters per second at an angle, which will actually be this angle right here, which will be 37 degrees west of north. Since we're going 4 meters per second north, and we're going 100 meters north, it will take us 25 seconds to cross the river.